11.7 essentially deals with the graphical analysis of functions. So everything we've learned to date, we want to kind of put into effect. First type of functions we deal with are the polynomial functions. And all the different features that impact the graph, you really want to know about and really need to kind of focus on. So let's look at the features of interest. I mean, first thing we know is the domain for the polynomials. That's easy. It's all real numbers. So the domain is, x is any real number. Very simple. Now the range, that is something that varies. So we have to use, we can find the range oftentimes approximately, sometimes exactly. But the range for the most is, you have to look at the graph and you find an approximate range for the most times. You can find exact range by looking at the shape of the graph and see what happens. And, this is mainly if it's an even degree polynomial. If it's an odd degree, we know the end behavior is going to be like that. This is odd degree. Or it could be like, this, with all stuff happening between. If it's an even degree polynomial, well, the end behavior could be up like this, or it could be down like this. What happens in between will give us our range value. So this sort of behavior deals with other things as well. So the other features that we definitely are curious about are its turning points. And that is related to the degree of the polynomial. Related to its degree. It's always, at least if it's an even degree polynomial, it has to have an odd number of turning points, and they have to be less than the degree of the polynomial. If it's an odd degree polynomial, it has to have an even number of turning points, and they have to be less than the degree of the polynomial. So if it's a fifth degree polynomial, it can either have 4, 2, or no turning points. If it's a eighth degree polynomial, it could have either 7, 5, 3, or 1 turning point. But that's what we learned about turning points. And that's related to the graph, the shape of the function in between the end behavior. This is all the end behavior. The other thing that's important is in between over here is its intercepts. Now the y-intercept is relatively easy. If I want to find the y-intercept, you just set x equal to 0, so that occurs at f of 0. Very simple. The x-intercept, that's where things get interesting. Where does it cross the x-axis? Well, that is related to the degree of the polynomial. Remember, we're finding, this is all about finding zeros. We did that in an earlier chapter. Finding zeros of a polynomial. And my suggestion is graph it. See if you can find a few of the exact values. Use long division to continue working with it until you find all the zeros. And we also have some cases where if it just hits the x-axis, then it's an even multiplicity. If it passes through and this kind of gets really close to the axis, it could be, it's always an odd multiplicity, but it could be of degree 1, 3, 5, or 7. So we learned early on when we were looking at how the shape of the function behaves near the end of it. We've established the end behavior over here. I'll put it again over here just so we know. The end behavior of the polynomials. We just wrote about that. And then the last thing that we like to do with the second to the last thing, we like to test for evenness and oddness. Test for evenness and oddness. Now remember, I'll put it over here. For an even function, f of negative x is f of x. For an odd function, f of negative x is minus f of x. Or neither. It doesn't have to be either one of these. Very rare do you get polynomials that are exclusively even or odd. More often than not, they are neither. But we look at that test for that. We want to see, that gives us some idea of the graph of the function, how it looks. And then the last thing we kind of like to do is, if we have a polynomial that's all written out, we'd like to write it in factored form. And with all this information and its graph, you have everything you need to know about that polynomial function, at least to the point where you can take it from calculus. So at the end, you might have some polynomial function that looks like this. I'll make some sort of a graph over here. And put some values over here of we have something like this. So we can see over here the end behavior goes plus infinity. So what does this look like? Well, we know it's an even degree polynomial. Only evens either go to plus infinity or minus infinity in the end. What degree is it? Well, I can estimate it to some extent over here. Look at the number of turning points. I have 1, 2, 3 turning points. However, this turning point over here kind of looks like it has if you look at that, that just touches the axis. So I could say that this is a factor, so that's a 0 of a polynomial. So we know for my f of x, put it down here, I have one factor that goes straight through. If it came down and went and then narrowly went through and then turned back around, I might say it has a higher degree. But when it goes straight through like that, it's like x plus 3 is a factor. Over here, that's passing through positive 2 straight through. So it says, well, x plus 2, excuse me, is a factor. And this over here says x minus 2 is a factor from that 0. Well, what about that one? Well, if I look at that one, it's just touches. So you can either put x plus a half, or sometimes you could just write it as 2x plus 1. And the 0 of that is negative 1/2. But that has to be in second degree here. Now, if it was flatter, I might say it would be 4th degree. So this is, in general, a factored form of that polynomial. Satisfies that end behavior. Same number of 1, 2, 3 turning points. Second, third, 4th degree. So you can actually build this polynomial in factored form. A lot of it comes out of just looking at the graph of the function. So if you know the graph of the function, there's many things you can kind of pull together. We usually like to write things in factored form. It's a nice way to look at it, rather than x to the 4th with some coefficient. Now, the only thing that's missing here that we don't have is we don't know what the lead coefficient is. That is arbitrary. That depends upon where it crosses, usually the y-intercept. If I know the y-intercept, then I can fill that in very precisely. Just plug in 0 for x, multiply everything out and make that A work out. And what you're going to deal with in the calculus, once you have polynomial functions, and this is what we've learned all throughout, so we learned a lot of material. Just finding these x-intercepts, there was a lot there. That's a fundamental theorem of algebra. You know, what do the zeros look like? What's the factored form? Now, in this case over here is, in calculus, you might look at when is this function increasing or decreasing. We're not going to talk about it here, but, you know, in the calculus, that's going to be critical. Now, when you're increasing or decreasing, you always go from the left to the right. So if I go left to right, I see I'm getting smaller in the y, so it's decreasing here, stops decreasing, increasing, stops decreasing, stops increasing, goes to decreasing and increasing. So decreasing, increasing, decreasing, increasing, and those intervals. What are those values over here? That is for the calculus to find out. We can estimate them using software like Desmos, but the calculus is going to show us how to do it exactly. Desmos actually uses the calculus to estimate those. And that's it. Polynomial functions, you want to find all those features. You want to state the domain. Can you approximate the domain? If it's an odd degree, the range is easy. It's all real numbers. If this happens to be an odd degree, then you have one extra turning point. We'll bring it down, and it'll kind of have, you know, this behavior as opposed to the other behavior. Turning points, that's related to the degree. It's always, you know, one less, and then it's even or odd. It's depending if it's the leading coefficient is leading term is even or odd. The intercepts are important. The y-intercept is very easy to find. Set x equal to 0, and there you have your y. You don't have anything such as asymptotes for these things. No asymptotes. You don't have to worry about that. But then all the stuff that we filled in. So in this chapter, it kind of encapsulates everything we did all throughout the course. All those things are needed to be applied over here. And over here, you might have to do some of that long divisions that we talked about. So that's a polynomial function. That's what you want to look at. Okay, and the next class of functions are the rational functions. I mean, to be truthful, polynomials are really a subset of rational functions. But since they have unique features, we kind of separate them out. So let's take a look at rational functions. And what are the things that become important when we analyze a rational function? Well, the more you know about these functions, the better off you'll be in all your, you know, courses. If you go on in your technical courses, but more often than not, you use mathematics to model these, and you pick them from a certain class of functions. Polynomials are very popular to use. Why? Because we know so much about polynomials and we know their behavior. There are some issues that I mentioned when, you know, the number of turning points can vary widely, and they're not great for interpolation sometimes and extrapolation, meaning going beyond and in between. They can have some problems if you raise the degree too high. They are used really well with interpolation when they're used for low degrees, like first and second degree polynomials. But then the other class of functions we have are rational functions. Okay, so what are the interesting features of these? Here we have the domain. Now this is where you can have some interesting aspects. Unlike polynomial functions, rational functions may have excluded values. They may have excluded values, and you have to check that out. And what do you need to check? To see if the denominator goes to 0 or not. Is that an excluded value or not? They don't always have it because, for example, say I had my polynomial or rational function that looks like this. They had x minus 1 over x squared plus 1. It's not a polynomial because I'm dividing by this, but x squared plus 1 never goes to 0. So in this case, the domain for this rational function is just all real numbers. because if I set x squared plus 1 equal to 0, I get x squared is equal to -1, so x is equal to plus or minus I. Well, that's not a real number, so it's not going to impact my domain. So I don't have that. So that is what's interesting with my rational function. You have to look, set the denominator equal to 0, and if it's 0, it's not in the domain. Then also that leads to the idea of the range. This is more complicated as well too. This is where you really have to look. There's subtle things that can happen. It looks like it might go plus or minus infinity, but it may not be. There may be certain excluded values, because you could have rational functions that look something like this. Here's some graphs of them. So you have a whole region here that may be excluded. So it's really subtle to find the output of those things. You have to look at the graphs. So the range becomes more complicated to find. And that's where we're going to need some of the tools of the calculus to find these more precisely. Although we can do it fairly nicely with Desmos. That's why I like that. It's a nice tool to allow you to visually understand functions, which is so critical in the calculus, because there's a lot of visual aspects. So looking at the picture is something that's important. Another thing that comes out that's very unique with the rational functions is the potential for a vertical asymptote or asymptotes. You can have more than one. We know that it occurs when the denominator is equal to 0, but just because the denominator is equal to 0 does not mean it's a vertical asymptote. So you have to test for it. So we have to kind of go through, because it's an excluded value, so it's definitely in the set of excluded values, but you want to make sure that it's not just one where you have a hole in the function, but you do have a line. For example, we looked at a function like this. X minus 3, x squared minus x minus 12. And put a plus 3 there. Here we go. If I put a plus 3 there, if I look at this, what do I get over here? So, oh no, minus 3. I did want minus 3. Give me a wink. My brain is wet the first time. So when I put in minus 3, I get 0 down here, but I get 0 up here. So for this case, this is nothing more than an excluded value. So if I looked at the graph of this function, and I went to x equal to plus 3, what you would see over here is the following. It looks something like this. Goes to 0. And you have to narrow it down. There's a little hole right here. And it looks like that. And it also has something on this side. I have my, if you will, should actually occur over here. Should be plus 3 and minus 4. Should look more like this. 1, 2, 3, 4. I'll kind of come over here and go like this. Over here, this will have a vertical asymptote at minus 4. But over here, I'm not going to have anything. It will have a little hole over there. So when I set this equal to 0, that's what I'm looking for. I read my excluded values. X squared minus x minus 12 equal to 0. That's one of the things we do. We factor that into x plus 3 and x minus 4. So I must have this set up over here. Yeah, so when I put it to be plus. Keep me awake. Yeah, so I got it backwards in my head. I did do it the second way. Because over here, then this would be a plus 3, so the solution to this is minus 3, so this switches over here. Switches over here. I should go to Desmos and look at this, but let's not. Let's put the correct values in there, because when we set this equal to 0, I'm looking at the two zeros, so minus 3 and plus 4. That's what I have to do. 1, 2, 3, 4, and 1, 2, minus 3. This is the part that is kind of missing over here. At 4, I do have indeed a vertical asymptote. So the graph of the function will kind of go, if I look at it this way, it looks something like this. For greater than 4. And then over here, what I have, I put in 0, so I get minus 1/4, so it looks something like this on the other side. So go around here. And over here, I have a little hole in the function. It's not a vertical asymptote. It's an excluded point. And you'll see that as you plug it into Desmos. So vertical asymptotes are an important feature of rational functions. And how do you analyze it? Set the denominator equal to 0. If it's an excluded value, then I have this. For example, I factored the denominator, so I get f of x equal to x plus 3 over x plus 3 times x minus 4. And that factor cancels out to give me a 1 over x minus 4. So this graph looks a lot like 1 over x minus 4, which is that, but the original function has that little point that you canceled out here, a little hole in it. So rational functions, it's a lot more complicated to analyze. In addition to the vertical asymptotes, we also have to deal with potential horizontal asymptotes. So what we have is vertical, and then we also have horizontal asymptotes. So we let x go to either plus or minus infinity, and we see f of x go to either some constant value as x approach some constant value. Could be 0, could be plus 1, 10, negative 6, something like that. Over here, we can kind of see over here, this should be if x was equal to 3. This should actually be underneath this. Yep, so this is my mistake here. A little bit underneath. And there it is. There's a hole here. So for this one, this has a horizontal asymptote of y equal to 0. Or f of x goes to 0 as x either goes to plus infinity or minus infinity. And when we're analyzing the horizontal asymptote, if the degree of the denominator was higher than the degree of the numerator, the horizontal asymptote is always y equal to 0. If they have the same degree, then I just take the ratio of those coefficients. So remember the subtlety of finding horizontal asymptote for rational functions. Kind of summarizing all the things we did so far. Because that's what I expect out of you, to kind of put all this together for the different types of functions. Now, those are the most important features. We also have over here the possibility as well as any intercepts, so you have to look at those as well. And we could also read back, the y-intercept is relatively easy. Again, you want the y-intercept, then you're going to work on f at 0, provided it's defined. For example, if you have 1 over x, it's not going to be defined, but for other things, if it is. And the x-intercept, that may lead us back to the fundamental theorem of algebra, because usually you're solving the case where the numerator goes to 0, so you just have a polynomial. So you set a polynomial here going to 0, as long as it's not an excluded value, as long as it doesn't get canceled out. So little subtle things along the way that you have to be aware of when analyzing rational functions. They are much more complicated than our polynomials, and within them they have all the complexities of polynomial functions. Now, we're not so much caring about the turning points and stuff like that, because the behavior of these can be really erratic and crazy, but those are the important features for your rational function. Okay, then after those, we did a little bit with radicals, but I'm not going to focus too much on radicals. We just really deal with the square root and sometimes the cube root. Most of the time it's of the radicand, or the argument of a radical function, is just a linear function. It's a basic linear polynomial function. But then after the rational functions, the next group are our trig functions. Now, over here for the trig functions, we're really dealing with, sine, cosine, and to a lesser extent, the tangent. Now, I'm not emphasizing the other types, they're reciprocal functions. I'll mention them here, you will see them in the calculus, but you'll see them less in terms of their graphs and more in terms of kind of using substitutions involving the trig identities. So you might have another function, which is the function that the reciprocal function of the sine. I mentioned them, but we didn't really go through them too much. Cosecant, the reciprocal function of the cosine, and the reciprocal function of the tangent. So we did not cover those to a great extent in terms of their graphs and their picture. You will see these more when you want to do when you're taking derivatives of these functions in the calculus. So this is where you'll have to do a little work. Some of the stuff needed to be removed. Now, I should point out that, like in Eastern Europe, they don't even teach these functions at all, because everything you need to know is in those three functions, and you just take the reciprocals and work with them. So in the Eastern Bloc nations over in Europe, they don't teach them. In a lot of other parts of Europe, they don't teach it. Why? Because it's only so much, and you could do a lot here, and we could spend another week on those, but this course is already jam-packed. So you may be a little weak on mainly the secant comes up, cosecant a little bit, but they're just the reciprocals of those. And notice, the way I remember it, C and S go together, so know which goes to which. If it's an S here, it's got to be a C here. C here, it's got to be an S here. That's how they switch each other. Okay, so those are the trigonometric functions we're mainly concerned with. Now, if we start looking at their features, well, again, we have things such as the domain. And if you're dealing with the sine and cosine, it's all real numbers. So for the sine and cosine, x is any real number. The tangent, however, has problems with its domain, because remember, the tangent is the sine of x over the cosine of x. And that has problems when the cosine goes to 0. You have, again, vertical asymptotes that's happening there. When you look at the tangent, it's problematic. So the tangent of x, my domain has some excluded values. It's a real number, but x cannot equal to plus or minus multiples of pi over 2. So like, 2n plus 1 times pi over 2, where n equals 0, 1. It's all the odd multiples plus or minus the pi over 2. It's a little more elaborate for the tangent. Now, the range is another important feature. For the sines and cosines, if it's just a sine and cosine, it's just +1 or -1. If I have an amplitude, then the range changes. If I have an offset, the range changes. But in this case, it's restricted in some way. It's either go to plus or minus infinity. We'll never do that. For the tangent, however, it will always go to plus or minus infinity, but then you also have to be careful about certain times when, values that, it goes to plus or minus infinity. It's the restricted values here that you may look at. But for the sine and cosine, if it's just f of x is just sine, then the range is the y, again, is a real number, the range, but y is between -1 and 1. If, however, I have a coefficient in front of that, then it can change. If it's 0.5, it goes plus or minus, it goes plus or minus 0.5. If it's 2, -2 to +2. So when we analyze a trig function, we're looking at the domain, we're looking at its range. Now the end behavior really isn't an issue. It just goes between, if it's just sine, cosine, 1 and -1. If it's a sine or a cosine, a and minus a. If it's a sine of x plus an offset, well, then you have to shift everything up and then see what it goes for. So the range there can change depending upon the functional form of the trig function you're dealing with. Now for the range for the tangent, plus or minus infinity. But these we've looked at all throughout. I'm kind of summarizing them here for us right now. The other thing we are also, considering here is any sort of intercepts. Now, if it does have an x-intercept, it will have infinitely many x-intercepts. So a lot of times we cut down the range and say we only want to find the zeros, the x-intercepts in a finite range. So that will limit the number of x-intercept to a finite number. But if I just say in general, it will, if it has one x-intercept, it will have infinitely many. It may not have any if you have an offset. So for example, say I had y is equal to sine of x plus 2. Well, what would the graph of that look like? I'll put it as f of x. Well, the graph would look something like this. And here's my, 1, 2, and 3. Notice I don't have any x-intercepts. The offset pulled it out. But if I didn't have that plus 2, so I just remove that, then it would look like this. And what do I have? I have infinitely many of those x-intercepts. Now the y-intercept, again, is easy. Just plug in x equal to 0, so that turns out to be 2. So the intercepts are important for these trig functions. What else? Well, just the other day we learned some other features that are very important for the sine and the cosines. Now you can also study the same thing for the tangent, but we did not. And we're leaving out things, for sure. There's only so much, but we're trying to include most of the things that are kind of critical for the calculus. So the other thing we have to deal with is the amplitude. The offset, if it has any. Oftentimes we don't have an offset, so we don't have to worry about it. It's kind of a rarity. We also have the period and the phase shift. So those are all properties, parameters, whatever you want to call them, that go hand in hand with the trig functions and their graphs, and trying to understand their graphs. You know, the period is very important. Phase shift also is important, especially if you're going to an engineering such as electrical engineering discipline. That becomes extremely important. And for the most part, that is what we need to know about trig functions. And they are used to model things that behave periodically. And my always suggestion is go with the graph first. You have that capability, put that graph in, you'll see a picture, and all these features will suddenly become apparent. You know, the amplitude, it's a plus and minus. So the amplitude is this distance over here, so its amplitude is just 1, offset of 2. The distance between these, that particular one, is 2 pi. That's my period. Phase shift over here, well, there's nothing adding or subtracting the argument, so this has a 0 phase shift. Phi is 0, so the phase shift is 0. So those are the things you should be looking at when you see a trig function. Okay. Then we looked at exponential functions. So then the fourth type of functions are exponentials. And we know for those, the domain is very simple. It's, you know, all real numbers. I'll write it very simply. Any real numbers work. The range, that's a little more problematic. You have to analyze that. What are the values that you can expect that'll come out of my, you know, f of x equal to some a to the x. Now you could write it more generally like this. You have an a over here, a b over here, and say a capital B over here. Have an offset. B might be negative, so you might have increasing, decreasing, all sorts of things that will impact the range of that. The sign of A will impact the range of that. So you have to be a little bit careful there. And the thing that is critical here, after you figure these things out, again, you may have the same thing, oh, this is B, excuse me, the same thing with the intercepts. Depending upon what B does, it could make this exponential function cross the x-axis. You will always have a y-intercept, and again, the y-intercept is when x is 0. So if you have a coefficient of a over here, setting x equal to 0, I get my intercept is going to give me a plus b. And you just set that in algebraically. So you have to look at the intercepts. And the last thing we look at over here is it has a horizontal asymptote. So these are the features you want to analyze when you're looking at a exponential function, to understand it through its graph. And plug it into your calculator, you see the graph, you can pull out all those features. And you should be looking for them. Because when you model some physical phenomena, these intercepts, a horizontal asymptote, they take on a new meaning. They mean something. And then that allows you to interpret results when you start using these functions to model. And the last big class of functions we looked at was the logarithmic functions. Now, these also have the same questions. The domain becomes a problem. So the domain has excluded values. Most of the time. Now, there are rare occasions where they don't. For example, say f of x looks like this. Take the natural log of x squared plus 1. I can put any value into that logarithmic function. Doesn't matter what I put in here. Because what happens is, if I plug in 0 for x, I get the natural log of 1, which is 0. So if you kind of looking at the graph of this thing, we'll kind of show you what that looks like on Desmos, just so you know. There's all these little subtleties that you have to be aware of when you're doing and getting ready for the calculus. Well, let's get Desmos over here. Okay, there it is. So we've covered a lot, but there's still little subtle things that you have to kind of worry about sometimes. So I take my y equal to the natural log of x squared plus 1. See what happens here? There are no vertical asymptotes. It comes down, and I can plug in 0. It just never goes negative. So in this case, the range is also limited. So it's not always plus infinity and minus infinity. Depends upon what's happening in that argument. A lot of little subtlety that you have to be aware of and cautious of. So I just thought I'd mention that and show that you do have to be careful when you're looking at these. And the same thing, you also want to be aware of the range. And the range, it depends. Look at the function. Like for this one, the range is everything is all positive or 0. So for this problem, the range is a set of all elements y is a real number, and y is greater than or equal to 0, as you saw from the graph there. Again, just like we have problems over here with intercepts, we have intercepts here. And also, what you might have to do is you might have to use the properties in both of them, of the logs and exponentials, to solve either a logarithmic equation or an exponential equation. And we did those when we were solving those equations. So that's where that skill comes into play. If you want to take and condense it into a single logarithm, and then you can exponentiate both sides and solve that to find maybe an intercept, something like that. Now, what's different than the exponential that is involved in the logarithms is you have the potential, not all the time, but 99.999% of the time, you have vertical asymptotes. If you have any excluded values here, you will have a vertical asymptote. At least one. Sometimes you can have more. But those are the features that you want to pick out of the graphs of these functions. So that fills in all our knowledge of them. So when you go to the calculus, you'll know how these functions behave. And again, you want to look at both of them. I'll mention over here, the end behavior. I'll put it over here. And the end behavior. So when we analyze functions of the different types, that is what we're concerned with. Notice in all of them, it's always the domain and the range. It's the top two that we want to understand. When you go to the calculus, you'll be adding additional features onto these things. So it's not just going to be these exclusively. We're going to add to it. So if you know these, you're going at the level that you need to be to add to the knowledge for each of those functions. For each of those class of functions, you're going to be finding intervals of increasing, decreasing, maximum, minimum, something called the inflection points of these graphs. Crazy new terminology. But you need to know all of this, so when you add that, you don't get overwhelmed. You need to be comfortable with this knowledge about the function, so when you get to the calculus and you start adding these new features that are kind of come at you from the calculus analysis, you're just adding to a list you already have and not constructing the entire list. Many students go into the calculus and have to reconstruct this entire list, and that's where they fall behind because they don't have the basic knowledge of these classes of functions and the features that are important for all of them. So in 11.7, we have a variety of different functions. There's some examples in the textbook. And all we're asking you to do is graph them and find all these important features. So, I've given you the list here. So when you do that, graph them, find their features. If they're polynomials, there's a lot of work you have to do in terms of trying to rewrite it in factored form. So all the things we've done allow you to put everything together to solve these sort of things. Now, in addition to here, especially when you're dealing with the sines and the cosines, when you're finding the intercepts there, then you may have to solve some trig equations. Because you might take, instead of just sine and cosine, you might mix them together. And you get crazy trig functions, which is a product or sum or difference or products of sines and cosines. And you can get very elaborate looking trig functions there. So you have to be careful. But that is essentially what this course is about. Trying to understand everything we can about functions, the different types, and what are their properties and what are their features that we need to be aware of. And we constantly repeated domain, range. That was always on our forefront. And then intercepts. We're always looking where they're going to intersect either the x or the y-axis, and how do I find it? The y-intercept, I just plug in x equal to 0 and compute the y value. X-intercepts, well, then I set the y equal to 0, and that becomes a little more problematic in terms of solving it. Sometimes there are no, x-intercepts or y-intercepts. So you may not have, and for example, this very simple function, rational function here, has no x or y intercepts. Looks like this. Now the domain of this is all real numbers other than 0. The range is also all real numbers other than 0. So little subtle things that you learn about these functions which will help you what's happening. The end behavior for both of these as x goes to plus or minus infinity is f of x goes to 0. Has a vertical asymptote and a horizontal asymptote. X equal to 0 is a vertical, y equal to 0 is a horizontal. There's a lot packed into this little function. But if someone asked you all those things, you should be able to rattle that off. You should get comfortable with that. There's a lot of techniques that we did in this course too. Techniques that you will need not only in calculus 1 or 2, but we did the partial fraction decomposition. We included that because that's something you will need in calculus 3, and we're doing it extensively right now in calculus 4, which is differential equations, with my differential equations class. We're doing Laplace transforms, and that is critical knowledge that you have to have. So we'll review it again at that point in time, but make sure you have some familiarity